Hi, good morning, or good afternoon almost. And thanks so much for having me. Thanks, Aaron. Cool. Everyone can hear me all right? Awesome. So, yeah, thanks again. My name is Matt Rube. I am the Vice President of Business Development at Heimdal. I know it's not always obvious how to say the name of the company based on how it's spelled, but it's Heimdal. It is a reference to Norse mythology, which is an homage to our founder's roots. He's from Norway originally. We're a company based out of Colorado right now, but here to talk about our first facility, which is operating in Shidler in Oklahoma, right up there. And we are doing direct air carbon capture. So we'll talk a little bit about the background to who we are as a company, how we got started, what the technology is and what we're doing. And we'll talk about what our plant in Oklahoma is for, how much volume of carbon dioxide we're able to capture, the goals with the Enhanced Oil Recovery Project in partnership with CapturePoint, and where we go from here. Talk about a little bit about carbon management and enhanced oil recovery. I won't try to get too much into the weeds on that because I think a lot of you probably already know about the history of using CO2 for enhanced oil recovery in the country, but I'll talk about that and I'll talk about how new technologies like carbon capture, direct air capture can unlock more enhanced oil recovery without the need for new infrastructure like pipeline development. Then I'll get into a little bit about Heimdal's differentiation versus other companies trying to do this. We're not the only ones trying to build new technology to capture CO2, especially CO2 directly from the air, and I'll get into why we are different from those other folks doing it. And then we'll finish off with sort of what's next, both for us and for where we see this industry going, the carbon capture and management side of things, and then the use and storage of that CO2 as well. We were founded in 2020. Our founder came over after graduating from Oxford with a degree in chemistry, had an idea based on that the chemical engineering research that he did in university about how to use a solid mineral to capture CO2 from the atmosphere effectively and efficiently. Went over to San Francisco at a startup accelerator, raised 11 million. You'll recognize some of the names up there probably. Sam Altman, who is now with OpenAI and doing the ChatGPT stuff. Mark Benioff at Salesforce, some other family offices, and venture capital as well. And then from that founding, spent a bunch of time in the lab doing research, refining the process, figuring out how to do it cost effectively, figure out where to locate, and coming up with our first facility, which we call Project Bantam. There's that beautiful shot of Shidler over there in our facility, and I'll talk a little bit about what it is we're doing, how our technology works. But essentially, we are a direct air capture carbon dioxide removal technology developer and operator. So we build facilities that capture low concentration carbon dioxide directly from the atmosphere. We take it and we are able to concentrate that CO2 to then use it or store it underground. We use a limestone essentially to do that. And I'll talk more about how the entire process works to capture that CO2 from the atmosphere and then concentrate it for use or storage. The main issue with these technologies prior to now is it's been too expensive. It's much more expensive to capture and much more complicated historically to capture low concentration carbon dioxide versus high concentration carbon dioxide, capturing it off of an energy flue stack or off of existing industrial high concentration processes like fertilizer development, like what they're doing up in Kansas. But we bring the cost down through a number of ways to around $200 per ton today and well under $200 per ton by 2030, and we have a pretty distinct pathway to those cost bases. And I'll talk a little bit more about why that works for us as a business model as well. It might sound still fairly expensive, but that's to the point where it's sufficient for us to be profitable as a company. It's also 5 times cheaper than our next closest competitor doing this work. And one of our main advantages, aside from the cost, is our flexibility of deployment. We can deploy just about anywhere with enough land. Our current facility out in Shidler is about 5.5 acre footprint that has a nameplate capacity of about 5,000 tons of carbon dioxide captured per year. Obviously, that's a drop in the bucket relative to the amounts that are typically used for industrial processes or enhanced oil recovery today. But we're hoping to scale up quickly through 2030 to more than 1 million tons a year. But 5,000 tons per year is our nameplate capacity on the current facility, 5.5 acres. We can deploy that size, and we expect to be able to deploy future sizes in 12 to 24 months, or 18 to 24 months, using a combination of our approach with the balance of plant, which is only leveraging mature off-the-shelf technologies that are available today, so no new supply chains are needed, and using limestone as the main feedstock for our process and carbon capture, which obviously there's no shortage of limestone here in Oklahoma. So affordable, available in lots of different areas, quick to deploy with supply chains that we know. And that's essentially how we're trying to make this work, where in the past it hasn't. So I have this nice little infographic about our process. Don't try to read the small text, it's a little bit too small. Process components is essentially an all walk through step by step. This is how we do it. So we start by getting limestone from any quarry that's located nearby. Currently we get most of our limestone from a quarry called APAC, located in Osage County. We can use any type of limestone. There's not a specific chemical property that we need, although certain types of limestone, depending on how much calcium it has, works better for our process. But we can really use any quarry and any limestone aggregate that's available, whatever is going to be the lowest cost and most effective based on the volumes we need in our proximity to available aggregate. We take that limestone, we put it through a heating process. We take a kiln, standard equipment from any type of lime manufacturing facility, similar to the kilns used in the cement industry. And we heat that rock, and think of the limestone as a CO2 sponge. So limestone will naturally absorb CO2 just everywhere, whether you use it in building materials, whether you pave it onto the roads. Limestone naturally reacts with CO2 in the atmosphere. We're just doing that process faster. And if you think of limestone as the sponge, and our process is making the sponge as capable as possible of absorbing as much CO2 as possible, the heating process is wringing out the sponge. So essentially we heat up the rock. That releases the gas in a concentrated form. That concentrated gas is what we then purify and send to partners like CapturePoint for use in enhanced oil recovery, or for subsurface wells for storage, or for other industrial uses down the road. So we take the gas off of the heating process that's concentrated, we purify it, we compress it, and then we send it for use. The rock material that comes off that process is cooled in a heat recycling system. And then we take that rock, and in a proprietary way, we mix it into calcium hydroxide granules. That's our optimized sponge. So essentially, there's no additives. It's basically still the same rock, but we've managed to convert it into a form after the heating that is optimized for absorbing CO2. It's essentially a mix of high porosity, so that airflow will make as much contact with the material as possible, but retaining a high degree of material hardness, so that we can leave it outside without it blowing away, without it being damaged or exposed to the element, or when exposed to the elements. And we've struck that balance well. We weren't sure how hard these granules were going to be when we left them outside, but they've survived the 50 to 60 mile per hour winds we had a couple of weeks ago out in Shidler. They've survived rain, they've survived ice, they've survived snow, and through all of those types of conditions, they keep absorbing that CO2. And so there's good airflow in these granules, but they're hardy enough that when we lay them outside across our field, which is again that 5-acre field, they just sit and react with the CO2 in the atmosphere to absorb it. In anywhere between 4 and 20 days, that material will have fully reabsorbed all of the CO2 that it can and becomes complete limestone again. So that reaction after the heating process and after we've converted them to granules is naturally reacting with the CO2 in the atmosphere. And once it's absorbed it all, it's just limestone again sitting on the ground. Once it's limestone again, we pick it up with standard front-loading equipment. We bring it back to the start of the cycle, the heating process. We wring out the sponge. We create concentrated CO2, and then we just loop it through that process over and over and over again. Wring out the sponge, absorb the CO2, and on and on and on. There's no chemical degradation that we've seen with our limestone material. So aside from missing a couple of rocks when we pick it up with the front loaders, we're not going to be losing limestone throughout the cycle of the process. We can keep using the upfront amount that we procure to continually do this carbon capture work. And then the gas is sent to our partners for use currently, or for storage down the road, or for other uses beyond oil recovery. But I'll talk a little bit more about that as well. That's what we're doing out in Shidler. This is our lead chemist, Will, taking advantage of a beautiful sunset to collect some samples of our granules on the ground. And as I mentioned before, 5,000 tons per year, yeah, that's really small. But it's currently the largest operating direct air capture facility in the country. It won't be. There's a bigger one that's getting commissioned in Texas soon. But for now, it's the largest. It'll be the second largest once that's commissioned in Texas. And currently, it's the second largest operating in the world. And we have a couple goals out there. The first goal, which should be the obvious one, we want to effectively do what we've said we're going to do and what we can do, which is capture that CO2 using our material and send it to CapturePoint for their EOR operations in the Burbank unit. We're capturing the CO2. We're still commissioning various parts of the equipment and refining the purity of the gas, but we're well on our way to all steps of part 1 checked off. And we're going to continue doing that for as long as we can. Second, and pretty important for new technology, we want to validate our cost projections for this. So I said we can achieve $200 per ton or around $200 per ton today. That's on a great day. We want to get that every day. And this is going to be a system with a lot of inefficiencies based on scale and because it's a first of a kind. We expect that. And so what we want to do is we want to see cost inefficiencies where we expect them and not where we don't expect them, and then identify any issues that we can solve for when we scale up. Third, closely monitor energy consumption. That's related to part two. The more energy we use, the more costly it is. We want to bring the cost down. But we also don't want to be using more energy than either we're helping produce or emitting more gas than we are capturing at the end of the day. So we're keeping a close eye on how much CO2 we're able to capture, how much energy we're using, and what the balance of that looks like over time. Four, we want to optimize the performance of our material to capture CO2. The more efficient the material is, the less time it takes throughout the year to capture CO2, and the smaller the overall footprint of the facility has to be, the more efficient we get the material. So we already have a baseline that we're happy with, but we're continuing to optimize for even unideal climate conditions. Because we are currently beholden to the broad swings of humidity, temperature, wind speed, and things like that for carbon capture, we want to create a flexibility of approach in our sorbent to ensure that throughout all of those conditions, we're able to do the work effectively year-round in lots of different areas as well. And so we're getting great data out there that our chemist is very, very happy with in all of those samples. And then importantly, number 5 is using all of those first 4 things that we are doing here in Oklahoma to inform how we scale up. And so 5,000 tons is small. The next facility is going to be 25 times larger. And then the facility after that is going to be 10 times larger. We're still picking out locations for that. We're still working on the engineering design, but we are in the development stages for both an 100,000 ton per year facility and then a 1,000,000 ton per year facility. And this is the team that's doing all of this work, both here and for those future facilities. This is Marcus Lima, our CEO. The Norwegian gentleman. He's helped by Chris Mitchell, our chief technical officer, who has more than a decade of experience in process engineering, and the rest of the team as well. Very accomplished engineers across the spectrum, as well as operators and me on the business side. And if you go out to our site, we love having people come around, see the site, take a tour, learn about what we're doing. It's beautiful out there, and we think our facility is kind of cool to look at. And if you do take that tour, you'll probably be getting the tour from our site manager, Lonnie Hicks, who runs the show out there and who's very accomplished. So that's us. That's a little bit about what we're doing up in Shidler. Now I want to talk a bit about carbon management and enhanced oil recovery. This is a subject that most of you probably are at least a little bit familiar with or experts in. So I'll try not to spend too much time on how it works or the history of it. You probably already know all that. But I will talk a little bit about how new technologies in carbon management like direct air capture can unlock more opportunity for enhanced oil recovery where traditionally it's been too tough. This is your basic diagram of CO2 injection for enhanced oil recovery. It's similar to other types of tertiary injection, but it's with CO2. And it's been around for decades. It was originally pioneered, I think, in the Permian as a technique, but now is spread substantially all over the country and along primarily the existing CO2 pipeline infrastructure in the United States. And that essentially looks like 146 million barrels or so of oil produced per year using EOR, or CO2 EOR specifically. And that's 139 projects using 79 million tons of CO2 per year along around 5,000 miles of existing CO2 pipeline. This is substantial, but it could be larger. And as anybody who's ever tried to build or work with or get connected to a pipeline will know, it's outrageously expensive. It takes a ton of time to try and build, and that's not even including all of the permitting hassles and the challenges that you face when trying to expand pipeline infrastructure in the US today. And so without any permitting reform, which is on the table, this will remain essentially as big as it is today without significant expansion in the future. But if there were infrastructure developments or technological developments that could expand access to CO2 and could be used in more places for oil recovery, that could produce up to 370 million more barrels per oil per year here in the US, and over time that could unlock up to 40 billion more barrels of domestic oil production and offset about a fifth of inbound oil that we import. And that's from some DOE sources, I believe. And so that's one of the things that we want to help unlock. is direct air capture. So we don't have to necessarily be along that existing 5,000 miles of pipeline infrastructure. We can co-locate with potential sinks of CO2 or potential EOR operations. In your conventional oil production, you emit about half a ton of carbon dioxide per barrel that you produce, and you leave oil on the table if you can't access it through some method of tertiary injection like CO2 EOR. But with enhanced oil recovery and the flexibility that we provide by being able to co-locate and capture CO2 from the atmosphere, you trap about 1/3 of a ton of carbon dioxide per barrel produced. You emit half as much CO2 because some amount of that remains trapped underground in that reservoir, the CO2 I mean. And with a ton of CO2, you access another 3 to 4 additional barrels of oil per day. And can produce up to 60% more oil with half as many emissions and extend the life of some wells by up to 25 years as a result. Cost competitive or superior, that's an important point. So a couple ways that we as a business can make money by doing some of this work. For every ton of CO2 that we capture from the air and use either in enhanced oil recovery or store in a well that is dedicated to subsurface storage of CO2, we can claim anywhere between $135 to $180 per ton. There's other industrial emitters that can also claim the 45Q at different rates for either use or storage, but this is the rate that's currently set. And there's a bill being floated around Congress to potentially up the incentive for using captured CO2 and enhanced oil recovery to $180 per ton as well. Again, incentivizing the use of CO2 to produce more oil here in the United States and offset some of that imports that I was talking about. So in the current administration, with a lot of emphasis on domestic oil production or domestic energy production, this has become sort of another priority for creating opportunities where previously they were too challenging to take advantage of. But I also mentioned just now the subsurface storage. There's a couple of different subsurface options that we're looking at. On the left is the EOR option. The CO2 is stored in an EOR operation. That's called a Class 2 well. There is also a program run by the EPA called the Class 6 well program. Class 6 wells are purpose-built for the subsurface storage of carbon dioxide. A bunch of states have looked into this for industrial emitters who are interested in doing something with their CO2 aside from just releasing it into the atmosphere. They aren't along existing pipelines. They don't have anything to do with their CO2 right now, but the incentive structure is there for them to store it if a storage option exists. And so these wells are in certain types of geological formations like saline aquifers where the CO2 once injected down will remineralize over time. They have to meet certain leakage monitoring requirements, but a lot of states are really interested in pursuing a Class 6 subsurface storage program on top of everything else. Various states, including Louisiana and Texas, Wyoming and North Dakota, among others, have requested what's called primacy to do the reviews for Class 6 wells on their own. If a state hasn't been granted primacy, the EPA is in charge of reviewing the applications for Class 6 wells. So a lot of states are also looking to take on the reviewing, permitting, and development process for Class 6 wells, and that interest is growing. There's hundreds of applications underway and pending, and dozens of primacy applications for states to manage that process on their own, including Oklahoma, which is starting to move in that direction. And the Geological Survey has been doing a lot of research, some of which in collaboration with CapturePoint, on what that could look like in certain parts of Oklahoma. So that's carbon management and EOR, some ability to unlock additional recovery, but we're not the only ones looking at developing carbon capture technologies to do this work. So multiple technologies exist to capture CO2. This is a pretty busy slide. Take a look through if you're interested, but the short version is all of them essentially do the same thing in taking CO2 from the atmosphere in dilute concentrations, something like 100 times lower concentration compared to point source emitters, using some type of sponge, whether that's a solid sorbent, a liquid solvent, or a metal organic framework or other types of approaches in order to essentially absorb the CO2 from the atmosphere in dilute form, and then some different form to squeeze the sponge depending on what the sponge is, whether that's electrochemical approaches, pressure swings, temperature approaches, or some mix of all of the above. And not every technology is created equal. We have some advantages that we think are pretty substantial based on the approaches that we've chosen. The limestone-based approach and the heat regeneration approach, as well as the balance of plant. One is that limestone's available everywhere. Some of the sorbents or solvents that folks use are toxic chemicals with complicated waste management requirements. Some of the approaches require substantial amounts of bespoke engineering that works well in the lab but doesn't work at scale. or a combination of all of the above, and we've tried to avoid that with our processes. So limestone, again, available everywhere, easy to work with. Kilns and calcination systems are also mature. They're used all the time in cement and lime production. So we're mimicking existing industries that have been profitable at scale and operate at economies of scale as well, so that as we grow, we take advantage of efficiencies in capital and energy use from systems that are designed to do a lot more processing than what we're currently doing today. Carbonation occurs passively. So again, those granules, we lay them out. We don't require an indoor setup with fans blowing air over the material or a vacuum sealed setup with fans blowing air over the material. Some of our competitors require those things. We've managed to cut our energy costs and the complexity of design as a result of not having to use energy inputs in the carbonation process, just in the regeneration process. And the rest of the balance of plant uses standard, well-known, well-tested, off-the-shelf equipment and operating procedures to function. And that works both at the current scale in Oklahoma and as we grow. And consequently, we're able to map a pathway to scale profitably with reasonable and known costs versus other folks who are having challenges in all of the sensitivities around their cost processes and having substantial supply chain issues and making it come together larger than in the lab. And consequently, that's put us at a cost advantage. The abundant input materials, the off-the-shelf components, and the existing equipment at scale, and the efficiencies of those equipment at scale from a cost perspective. And these are some of the other companies doing similar work to what we're doing today. Carbon Engineering, you'll see, is the closest. They're now owned by Occidental Petroleum. They're also building a 500,000 ton facility in Texas. But after that, there's us on a cost basis. So talking a little bit about what's next. There's a way that we can be profitable with the 45Q if we are below $200 per ton consistently by 2030. However, there's other ways that we make money as well, and we see this as a commoditized industry. So on top of the 45Q, the incentive that we get for enhanced oil recovery or utilization of the CO2 in some other form, we can sell carbon credits if we store the CO2 or we use it in other ways. And the carbon credits that we sell are to companies like Microsoft, to Amazon, to Meta, some big tech companies, some airline companies that are beholden to European regulations around the carbon emissions intensity of the fuel that they use and the flights that they take, and other transportation systems. And the carbon credits that we sell are for the net benefit of the emissions that we capture. So that's part of the reason why we take such a close accounting of our emissions and energy use from start to finish, is because net what we capture, net of the energy we use and the emissions we create, we can charge a price for that and sell it to companies that are emitting to offset those emissions. So we sell carbon credits on top of the benefit that we get and the incentive that we get for using our CO2 for things like EOR. But we see that as a short-term solution. We think that this is a commodity industry. It has been traditionally. There are a lot of uses for CO2, and then there are additional ones that are coming as well. So some research-based approaches include use of CO2 in alternative fuels and fuel feedstocks. There's enhanced oil recovery, as I've been talking about. There's uses of CO2 in chemical and industrial manufacturing. There's uses of CO2 in concrete that stores some of that carbon dioxide. And then there's other ones that you probably know about, like Coca-Cola is interested in sourcing CO2 from folks like us for carbonating your soda. Tyson uses CO2 for its refrigerants in its chicken nugget plants, or its chicken manufacturing processes. And so folks like that have also reached out to talk to us about what we do, how we capture CO2, the volumes that we have, and how they could work with us. And so down the road, there's EOR to unlock energy here in the United States, and then there's a variety of other uses for our CO2 that we see as a pathway down the road that as we expand, we can meet growing demand for CO2 pulled straight from the air. And that's on top of everything else. And these are some of the companies that are looking into those various types of approaches. And in order to meet that demand, we have the scale-up timeline. It's pretty simple and purposefully lacks some detail, but essentially 100,000 tons per year is the next step in that process. By 2027, we expect to be in the commissioning processes for that scale of facility. And for reference, current facility of 5,000 tons per year is about 1,200 or so cars worth of emissions per year. 100,000 tons per year would be about 25,000 passenger cars worth of CO2 per year. A million-ton facility is approximately the same as 250,000 cars per year. And at the smallest scale, we think 1 million tons is where we want to start replicating this facility all over the country in lots of different places. And we want to be doing millions of tons of carbon dioxide removal and use of that CO2 per year by 2030. So sometime in the next 5 to 6 years. And that's where we're headed. Thanks very much. And any questions? Yeah.
How does your sales stream purity, I mean, what specs do you have to get to for the CO2 injection, and then how does that compare to what they're currently buying from the coffee mill?
Yeah, absolutely. So it varies depending on who you're talking to. So the folks over at CapturePoint, John is here today, so you can always talk to him if you have more questions about their processes. They give us a spec sheet for what they need the CO2 purity to be, and we try to match that as closely as possible. So what we're blending into the existing stream from the Coffeyville plant, we try to get to as close a degree of purity as what they have as well. The kiln that we use influences the purity that we see right off of it and how much additional refinement we need to do. It's an indirect fired kiln, which means that we see, we're trying to get basically 90% plus purity with as few impurities as possible. But the exact breakdown of that spec sheet, you'd have to ask him. I don't know the full details. We try, but it's different for everybody for every different use and every different storage case. Yeah.
What was the smallest scale you can do right now? So we all look, we have all these small operators all across, Oklahoma.
Yeah.
We already have this, infrastructure across our, U.S. land where we have all these well sites. We essentially what we have here possibly make these a carbon neutral well site.
Yeah.
If we can scale it to, hey, we could use the current well bore that we were going to plug and abandon, maybe repurpose well bores for storage. Also, we could look at maybe using methane emissions to power a generator, power your facility, something like that, where we can get it out. Not so much like we really need to build the largest facilities, or we need to scale this, to smaller pads and footprints, where all of our well sites might be, additionally, because we're seeing how we're adding assets to all these well sites, or maybe small data centers, and each one of these is its own little microverse across the nation.
Yeah. So the question. Yeah, the way that our process works, the smallest scale that we could reasonably do is still probably in the hundreds of thousands of tons of CO2 per year. The way that we've set it up here in Oklahoma is not a sustainably scalable system based on the equipment that we're using. It's not meant to be used at 5,000 tons per year. We've sort of retrofitted it for our first facility and for research purposes. But 100,000 ton per year facilities, we could pop up all over the place, and depending on the volume of offtake that would be available. Anything smaller than 100,000 tons of CO2 demand per year across various sources or end users would probably not be worth it for us. That differs though. Some of the companies that I mentioned before, they operate better at smaller scales. Yeah.
How are your plants? What type of electricity do you guys have? Gas?
Yeah, so the heating process uses natural gas. And closely monitor how much natural gas we're using and what the CO2 looks like off of that. In future facilities, we are looking at using natural gas for the heating with point source capture, depending on the type of kiln that we use. There are some types of kilns as well with different trade-offs. There's kilns powered entirely by electricity. Those aren't quite mature enough yet for what we want to do. But natural gas powered for the kiln, and then grid electricity for the rest of the balance of system. But the grid electricity is very minuscule in terms of use compared to the heat that we have. Yeah.
Just to follow up, so do you buy or do you buy the gas from the operator?
Yeah. Yes, that's right. Well, we buy the gas from the utility providers that are available. So when we're looking at the power purchase that we need to do on a facility-to-facility basis, it's based both on the fossil intensity of the grid emissions that we're going to be getting, the natural gas availability in the region, who sends that gas along pipelines that are available. But that's a site selection criteria, is just availability of energy. We're not married to any specific type of kiln technology or energy feedstock, so we can adjust that on a plant-to-plant basis as well. Yeah.
So when you're producing the oil in these EUR projects,
yeah,
and you get this associated gas that comes out, and it would have a certain amount of CO2,
yeah,
how do you separate, and capture that CO2 out of the gas stream?
Yeah, so in the plant I'm talking about up in Oklahoma, because it's an indirect fire kiln, we don't capture both streams. We only capture the stream off of our material.
You don't capture that gas?
We don't capture that gas here, but in the future we will. Correct. But in the future, we will capture the CO2 off the gas as well. We'll have a direct fired kiln with a point source capture system on the tail end of it to capture both the emissions off of the natural gas that we use as well as the emissions off of our material that we've captured from the air.
Floods, don't they use like a refrigeration method to pull the nitrogen back out of the gas stream?
This is a little bit above my head from an engineering perspective, but yes, there's ways of pulling various types of gases out of the gas stream, whether that's impurities that we don't want in it or the CO2 itself.
Scalability completely dependent upon the surface area that you apply the limestone to?
Yeah, so the heuristic that we found based on the efficiency of the material we use up in Shidler is about 1,000 tons of CO2 is capturable per half acre using our material. So from a land use perspective, that's our heuristic. We look at sites with, somewhere above 200 acres for some of these mature facilities that we're looking at in the short term. The rest of the limitation is based on the kiln technology, the amount of rock that kiln can process in tons per hour, tons per day, the efficiency of the rock material based on where we're located. But yeah, it's about half an acre per 1,000 tons per year from a size use perspective.
How long does it take for the CO2 to get back into the rock setting outside?
Somewhere between 4 and 20 days. So trying to get, that depends on the climate conditions. The hotter it is, the more humid it is, and the higher the wind speed, the faster it is. So on a typical day like today, 4 days in Oklahoma. During the winter, that'll slow down to something like 20 days. And as the summer months continue and as it gets even hotter and the humidity really ratchets up, we'll see if we can even get it down past that. But somewhere between 4 and 20 days, and that'll just depend on time of year. And as we continue, we'll try to optimize to get that as short as possible. Yeah.
The 45Q tax credits,
Yeah.
I remember being like $65 a ton for EOR.
So that's for emission sources off of an industrial emitter or from a natural gas source. So if you're a combined cycle, or not a combined cycle plant, if you're using a power plant with a point source capture system on the tail end of it, or if you're the plant up in Coffeyville and you're claiming the 45Q tax credit, that's going to be somewhere between $85 per ton and perhaps lower depending on how you capture and what you're using it. But it is lower. If you capture and use using our process, so direct air capture from the atmosphere, because it's a newer technology, because it's still maturing and they want that technology to grow, the incentive is a bit higher. So that's the $135 to $180 per ton.
Do you see that tax credit changing, or you mentioned that it might go up?
Yeah. Do you see it getting cut? Yeah. So it's a good question. There's a lot of investment that is being partially supported by that tax credit, and not just by us. So there's a lot of projects that are under development right now in all over the country, whether that's in Texas or parts of Louisiana, parts of Alabama, here, that rely upon the 45Q in order to make some of the upfront investment in reaching the final investment decision worth it. Congress understands that. We've had a bunch of conversations with folks on the congressional level as they've re-looked at all of the tax credits to evaluate how they see it, let them know what the differences in the economics are, why we think it's valuable for that tax credit in particular to stick around, and they've been very receptive. One of the reasons for that is the 45Q predates the Inflation Reduction Act, or the IRA, so it's not a Biden-created tax credit. The 45Q has been around since I think 2007, and it was actually under the first Trump administration that the tax credit was initially expanded. And consequently, it's something that everybody's familiar with. It's not new. It's received a bunch of support historically. And so the sense is that among clean energy tax credits, or at least perceived clean energy tax credits, this one is seen as one of the most secure. And it could be expanded as well, depending on how they want to shift the incentive for use of that CO2. But it's a good question because no one really knows. I think things change day to day, I would say, from that perspective. Yeah?
What's the difference between a new piece of limestone and one you reuse? How long do they give up?
Yeah.
Eat and drink CO2.
We actually find that the recycled material is better than the fresh material. We're still dialing into the exact chemistry as to why that is, but we have a couple of theories. One of which is in the process of creating these granules, there's some degree of rock crushing involved, and there's some amount of reconfiguring of the material internal matrix to crystallize as much as possible. The reaction of the material is called an adsorption reaction, and essentially means that the more surface area the material has exposed to CO2, the more effective it is at making that absorption process happen quickly. And so what's called the Xmax, which is the total amount of CO2 that each particle or square meter of material can capture, that Xmax is actually higher after we've done the process a couple of times. And we think it's because we enhance the crystal structure on a microscopic level of the material with our cycling process. And so the physical structure actually improves for our process over time, not gets worse. Which was a nice one. We didn't expect that, so we're happy to see it in real world practice. Yeah?
So given that you're capturing CO2 from this ambient air,
Yeah.
if you scale up to these large facilities, is there any possibility of that being a negative impact on offset agriculture?
Yeah, that's a great question. The answer is no, because even the amount that we would capture at our largest feasible scale wouldn't have a meaningful impact on the concentration of atmospheric CO2 in the region on any basis. So this is, again, millions of tons of CO2 per year, potentially, in one area, but that's per year. And again, even a 1 million ton per year facility is only the amount of 250,000 versus the millions and millions of cars on the road today. That's not accounting for any other emission sources. So we're not going to run out of CO2 anytime soon, and the localized impact is negligible. And we are currently monitoring both on site, and we plan to monitor in the future lots of other ecological impacts from our facilities being out there. That includes air impacts, but it also includes soil impacts. Farmers use limestone to enhance the alkalinity of their soil. And so we want to take a look at, over time, how soil alkalinity around our facilities, because we use limestone, could actually be beneficial, potentially, as well as sort of the different gas compositions from both environmental sources, atmospheric sources, and our process in general. So short answer is no, and we're looking at any other potential environmental impacts, both harmful or beneficial, that are unintended.
What's the current concentration of CO2 in the air today? I know it's been going up slightly every year.
The average in the world is 420 parts per million in the atmosphere today, which I think is about double pre-industrial levels at this point. So pre-industrial levels, it was in the 200 to 300 parts per million range, and now we're in 420 or so. All right. Thanks so much again. Really appreciate it.